Thank you, Anders. So my name is Lars, and I work for IOHK, for those who don't know us. So we are heavily involved in blockchain and cryptocurrency technology. And I'm the director of education. And I didn't put a $ on my tag, but we are always looking for good people. So if you're interested, you should check out our homepage. Okay, but this is, even though it's related to what we do, it's a personal project. So authenticated data structures. So what do I want to talk about? So first I want to briefly explain what they are and why we care, and then give the prime example or the canonical example, that's Merkle trees, and then show how you would do something like Merkle trees ad hoc by hand in Haskell. Then there is a great paper by Miller et al. That for OCaml, they show how to do this generically. And then I show how you can adapt that to Haskell and do it in Haskell. And I show how this simple example can be converted to use this generic framework. And then eventually I show a second example, authenticated lists, and a little demo. So let's start with what they are. So to quote Miller, an authenticated data structure is a data structure whose operations can be carried out by an untrusted prover, the result of which a verifier can efficiently check as authentic. So we have two parties, and the verifier and the prover. The prover does the actual work, and the verifier is interested in the answer, but he wants proof that the answer is indeed correct. So, right. And just to give an idea how that can possibly work, it uses hashing. So I will come to what that is in a second. But the core idea is it uses cryptographic hashing. And basically, the verifier, all the data the verifier needs to hold is certain hashes. And then the proofs that the prover sends to the verifier to prove that the answer is correct basically involves the pre-images to certain hashes so that the verifier can check that the prover indeed holds the correct data. And so what is a hash function? It doesn't really matter what in detail, I mean, which one we use. There are many, but it's a function that takes arbitrary bit strings to bit strings of a fixed length. So the input can be arbitrarily long, but the output always has a fixed length of bytes or bits. And we want the following additional properties. It should be collision resistant, which basically means it's injective. And obviously, a simple counting argument shows that it can't really be injective because, as I said, the input is arbitrarily long, so the input is potentially infinite. But the image consists of these fixed length bit strings, so there's only a finite number of possible hashes. So obviously it can't be injective. But in practice, it should be injective. So it should be very hard to find two elements in the domain that are mapped to the same hash. And it should also be hiding. That means basically given a specific hash, it should be infeasible to construct a pre-image to that hash. So the only way in practice to find a pre-image should be to search, just exhaustively search the domain until you find a pre-image that maps to this hash. And there are plenty of examples, as I said. Some have turned out then, some hash functions that were popular have turned out to be not secure in that sense. So people have found two elements that map to the same hash, and that's then even published, so that's normally big news. Right, and in Haskell, there are, of course, many ways to do that. I'm using the Kryptonite library that's maintained by one of my colleagues, and there is a long list of hash functions that's supported now for this. For these slides, I picked MD5 because that's relatively short, otherwise the hashes don't fit on the slides. In practice, you would probably use something like SHA-256 that has 256 bits hash or something even stronger. So it doesn't matter, so I just assume I have a data type hash, and a function that can, I mean, on the previous slide I said a hash function maps bit strings to bit strings, but of course in Haskell we want richer types, so I do it for every A that has a binary instance, and then obviously I mean it's implemented by first serializing using the binary instance and then applying the hash function. And then you can, I mean, strings and integers are, of course, binary, so you can do it, and then that's what it looks like. Okay, and so as I said, the canonical example where this is used is Merkle trees, and the prominent use case is Bitcoin. And I mentioned the prover and the verifier before. So in the case of that use case, the prover would be a so-called full node, so some desktop machine or laptop standing somewhere has a lot of memory that holds the data of the whole blockchain, which in Bitcoin's case is hundreds of gigabytes. And the verifier is probably a mobile device, some lightweight client that is too small to save the whole blockchain. And if you want to use Bitcoin to buy a coffee or whatever, then you have your cell phone and you use some app, and then the guy that sells you the coffee wants to be sure that you actually paid. So this Bitcoin transaction should be verified. So it should be in the blockchain. But in order to really check that, you would need the whole blockchain, these hundreds of gigabytes, and you don't want to. So this is a perfect use case for this prover-verifier scenario. So the mobile client queries a full node that holds all the data, and the full node then says, yep, that transaction is there in the blockchain. But it includes a proof that this is indeed the case. So the prover can't lie, because otherwise you could cheat people out of coffee, right? If you could somehow get the prover to lie about this. And how does it work? I mean, I won't later use this exact example of Merkle trees, but it's very similar. So the idea, as I said, involves hashes. So you have this binary tree structure, in principle a complete binary tree, so all the leaves, everything has the same depth, and each node has exactly 2 children. But of course, in practice, it will be a little bit more complicated. So in this example, we have 4 leaves that correspond to transactions. So in this block, 4 transactions are included. And each node is annotated with a hash. And the hash for the leaf nodes is just the hash of the leaf value. So these 4 bottommost nodes have just the hash of the 4 leaves. And then for an internal node, the hash of the internal node is a combination of the hashes of the 2 children. So you take the hash of the left child, the hash of the right child, combine them, hash this pair, and get the hash of the internal nodes. And in particular, you get the hash of the root, and the hash of the root is the only thing the verifier needs. So instead of storing this whole tree, the verifier, the cell phone app, only needs this one number, the hash. This is the so-called Merkle root, so the hash of the root of the Merkle tree. And if now, for example, the verifier wants to know is L2 included, then the prover will not just respond with yes, it is, but it will give a proof. And what does the proof look like? It will, so it will say, yes, L2 is included, and it's a right child, and the left child has this hash. So it will say it is a right child, and the left hash is this. And then it will say, OK, and then it's a left child, and the right hash is that. So it will basically walk up the tree, and then depending on whether it was left or right, always report what the hash of the other side was, where the thing was not. And then the verifier can check, OK, he knows the L2, so he knows this hash. The prover has reported that hash. So the verifier can combine them to get this hash. The prover has reported that one, so the verifier can combine and get to that hash. And then the verifier can compare that with the Merkle root he knows. And if that's the right answer, then he believes the proof, and otherwise he doesn't. And Of course, that's not a proof in the mathematical sense, but it's a proof in the sense of this cryptographic hash function. So in order to cheat, the prover would have to construct a collision, a hash collision. And if we believe that the hash function is secure, then we can also believe these proofs. So that's the idea how Merkle trees work. And I want to choose a slightly similar example, but slightly different. So let's look at this very simple binary tree type. So we have tips that carry data, and we have internal nodes, left and right child. And then I want to have a type that describes a path through such a tree. So I just have a direction type, left or right, and the path is simply a list of directions. And now I slightly modify the problem. So instead of the question being, is a given leaf in the tree, I want to look at the function lookup that gets a path and a tree and returns the leaf. And for this talk, I ignore all the, I mean, obviously, this can fail if the path doesn't have the right length or if certain children are not there and so on. So I ignore this for simplicity now. But of course, that's bad practice to do that in real code. So very simple, if we forget about provers and verifiers, just a simple exercise for, if you begin with Haskell. So how would you do that? Well, if your path is empty, you must already be at the tip. So you just return the value at the tip. And if it's not empty, then you are at an internal node. So then you, depending on what the direction is in your path, if it's left, then you recurse into the left subtree. If it's right, you recurse into the right subtree. So that's very standard, and therefore this example tree that's drawn there on the right-hand side, if you look up the path left-right, then then you go left and right, and you get to the 2, and it reports the true. Okay, this has now nothing so far to do with provers and verifiers. So now let's change that so that it has this property. So following this Merkle idea, we define a hash prime function that hashes a tree. And if it's a tip, we just hash the value at the tip. And if it's an internal node, we take the hash prime of the left child and the hash prime of the right child, form the pair, and hash that pair. And with those definitions, first on the prover side, so now we again get a path and a tree, and we produce the answer, but we also, yeah?
How does the verifier in the previous slide, how does the verifier know the tree's modified hash?
That the tree is what like that?
The second, in your second line, how does the verifier know the modified hash?
I mean, I haven't talked about the verifier yet.
The text says the verifier only knows the tree's modified hash. How does it know that?
Well, I mean, that's his data. I mean, that's his input. He gets the hash of the root. I'll come to the code for the verifier 2 slides down the road. But as I said here with Merkle trees, this light client, the cell phone app, only has this Merkle root. And that it downloads from the blockchain. So it basically, it doesn't download the full 100 gigabyte blockchain, but it does download the headers basically of each node. And the header contains that hash. Yeah, something like that. Yes, I mean, it must believe that that is correct, of course. Somehow it must get that from a trustworthy source. Yes. Okay, right. So now the prover, so it's supposed to answer this question, return the A, that's at the end of this path, but also return a proof. So in the tip case, there is no proof. And in the node case, so it recursively, as before, depending on the value of d, recurses left or right, gets a proof of the recursive call and the answer, and then returns that answer, but prepends the hash prime of the left and the right to the proof it got recursively. Right? So for each internal node, it includes the hash of the two children. It's very similar to what I explained about Merkle trees, but not exactly the same. I mean, in the case of Merkle trees, we only included one hash, and I mean complementary, whether we went left or right, but here, both. Right, and if you do that for this example that I had before, same tree and same path, then it returns the 2, but it also gives these 2 pairs of hashes. So the first pair is the hash of this and of that, and the second pair is the hash of this and of that. Okay, so following the path, always each internal node, the hash of the two children. Okay, and what does the verifier now do to verify? So this is the verify side of the story. Well, in the case of a tip, it just has to check. Okay, and the input is, so the path, the hash, which is the hash of the root of the tree, and it gets the answer of the prover, and it has to decide whether the proof is correct and the answer is correct or not. And so in the case of the tip, the tip, so the hash that the verifier has is the hash. So all he has to do is compare whether A hashed is indeed the hash it holds. So in our example here, if the whole thing would only be the 1, then the verifier would hold this hash, and it then just has to check that hash 1 gives this answer to know that 1 is the right answer. Okay, and in the recursive case, it looks at the first part of the proof, the L and the R, and it must check that its hash is indeed the hash of the pair of L and R, and then recurse in the rest of the proof. Okay? And if we try that with our example, then indeed, so if we do the same path and feed in the answer of our proof function, and we give it the hash of the root of our tree T, then it indeed answers true. And if we do something else, if prover and verifier don't fit together, if, for example, we call the prover with a different path, then the answer is false. So the verifier detects that this is not the correct answer. Okay? So this is very similar to the Merkle tree idea. And so what do we have? So it's obviously more efficient for the verifier. I mean, the verifier, all it needs as input of the tree is this hash of the root, and not the whole tree. And in this small example, if you look at the size of the proof, I mean, that was these 4 hash values in my example. Of course, those 4 hash values together are much larger than the original tree. But if you think of a really big tree, then the size of the proof obviously is linear in the height of the tree, in the length of the path, whereas the whole tree is exponential. So you see that for large trees, it makes a difference, and the size of the proof is much smaller than as if the verifier would have to hold the whole tree. So that's nice, that's what we want. And you could prove, or you can think about it and see that that's correct, that if the prover wanted to cheat, so give a wrong answer and a wrong proof, then it would construct a hash collision. So if there is a situation where the verifier answers true, even though the answer was false, then you can use that situation to construct a hash collision for this hash algorithm. And then you can publish a paper and be famous. So we believe that won't happen. Okay, so that's nice, but what is not so nice, I mean, if you look at the algorithms for prover and verifier, they are very similar. I mean, the structure is very similar. I mean, we have this tip case and the node case, and in the node case, we have to decide whether it's an L or an R, the first element in the path, and then recurse. And we do more or less the same in the verifier. But I mean, we have to write, and I mean, the original function, when we didn't care about verifiers and provers, was very simple and also looked like that. So we basically have three very similar things. There's just noise with these proofs. But now, where we want these proofs, we had to create these two separate versions for the prover and for the verifier. And of course, we have to concentrate very hard that they really fit together. And if we want this security guarantee here, then we have to actually prove that. And of course, we could make a mistake, and that can be a very costly mistake if it's not only about coffee, but something more valuable that you buy with Bitcoin, for example. And we had to come up with this hash prime. So we had to think, okay, left child, right child, we form this pair and then do the hash of that. So we couldn't just use the built-in hash or the hash coming from Kryptonite. We had to somehow modify it slightly. And the biggest disadvantage, I mean, this was now for this specific tree type and this specific algorithm to look up given a path. But I mean, of course, there are many more things like, I mean, the Merkle tree example is slightly different. There we don't have a path, but we just basically have a value and want to know a Boolean, is it included in the tree, yes or no? Or we can, of course, think of other tree types, maybe balanced trees, where sometimes a rebalancing happens, or maybe we don't just want to query the tree, we also want to build the tree, like include, insert elements, not only search for them or look them up, or other types, map or sets, or all sorts of things. And it's certainly possible to use this idea and somehow modify it, but then for each use case, we would have to do this mental exercise again. How do we do that with the hashes? What exactly does a proof look like? How exactly do proof and verifier work together? And we always have to write two functions for the prover side, for the verifier side, and basically prove that it's indeed secure. And there is this paper by Miller, Hicks, Katz, Shi, Authenticated Data Structures Generically, where they address these questions or this problem and ask this question, how could that be done in a nicer way that it works for many more data structures and for many more query types, and that you only have to do the proof once that the general scheme works, and then basically you get it for all sorts of data types for free. And unfortunately for us, they did it in OCaml, not in Haskell. And also they, okay, and I should also mention they modified the OCaml compiler actually. And the basic idea, their basic idea is they extended the OCaml type system by adding a new type lambda A for each OCaml type A. I personally find lambda is a bit overloaded, but anyway, that's their notation. And so once they have that, they also formally add to the type system functions for each type from A to lambda A and from lambda A to A that they call out and unout for authenticate and unauthenticate, which are inverses to each other. So it's more or less identity. And then they change the compiler, as I said. So they get two versions of the compiler. And then the idea is using these new types and the functions auth and unauth. You define your data function, your data type once. You write your function once. And then you use the two new compiler versions. And the one version gives you code that is the verifier code, and the other version gives you code that's the prover code. And by construction, they fit together, and by construction, they have these security guarantees that if the prover can only cheat you if he finds a hash collision. And what I want to do is explain how you can do that or something very similar in Haskell without having to hack into the compiler. And right, and I also want to use that as an example for free monads, but you could do it differently as well. I mean, it's just one way to implement this. So what's the idea? How does that work in OCaml? So we have this, for every type, we have A and we have this lambda A and functions out and unout that morally at least are inverse to each other. And on the prover side, this lambda A is just A. It's like a new type. Whereas on the verifier side, it's hash. On the prover side, out doesn't do anything. Whereas on the verifier side, it hashes to get the hash. And the really interesting part is the unauth. So on the prover side, to get the result of unauth, the prover doesn't do anything, but as a side effect, it writes X to the so-called proof stream. So the prover produces a proof stream, a byte string, that the verifier can consume. So in that sense, it's complementary. So when the prover and the compiler for the prover sees an unauth X, it just removes the, because it's the identity, so the value is clear, but then it takes that X and writes it in the proof stream in serialized form. And on the verifier side, I mean, there it only has this hash, but unout is now supposed to produce an A, but it only has a hash. So, I mean, there's no way to get from the hash to the A. That's one of the properties of hash functions, and that's where the proof stream comes in. So then the verifier takes the next chunk of the proof stream and deserializes it, checks that this deserialized thing's hash is the hash it had, and then proceeds. So that's how it works in OCaml. And that's how we want to, what we also want to do in Haskell now. Okay, and so first we define this data type. So instead of lambda, yes? I mean, no, of course, when you run the program, then that happens. So the verifier calls I mean, you compile it, and you have two versions. One is deployed somewhere to the server, one is on your phone. And then when you run the program, then the prover constructs this proof stream and sends it to the verifier, and the verifier consumes it. They prove that if you use their compiler, then it matches together for every program. Right. So in Haskell, I didn't call it lambda. I call it capital auth, this type constructor. That's basically their lambda. And I have two constructors, one for the prover version, one for the verifier version. And as in the original paper, the prover version is just a wrapper around A, and the verifier version just holds the hash. And then this helper function, so given such an auth A, I can extract the hash. So if it's already a hash, then I just return the hash, and if it's an A, I hash it. And using this, I can write a binary instance for auth A, and this is crucial now. I mean, even though A is serializable, and even if I'm in the prover version, I don't just serialize A, instead I send the hash. And so I always just send the hash, and the get is just, it deserializes the hash. So if I serialize and then deserialize, I always go from the prover version to the verifier version. And that's exactly also, I mean, that's very important, because in our tree types or whatever, in our data types, there will be these auth nodes, or I mean, we will see that later in a second in an example. And obviously, we don't want to send the whole data structure serialized over the wire. Then the proof would be just as big as the original data structure. But by doing this, whenever we reach an auth somewhere in the recursive data structure, it basically gets truncated, and all we send is the hash instead of the whole thing. That's why it's efficient. So let's see, before we see free monads, so I promised that this talk's also a demonstration of free monads. So briefly recap, so this is the definition from the CMET library, free. Sorry. So it's parameterized over type constructor f, which in practice is always a functor. And pure basically corresponds to return. And then we have this free constructor, which wraps in the given functor f recursively a free fa. And that's always a functor. And the interesting thing is that if f is a functor, then free f is a monad, free monad. So that's a way, given some operations that we represent in the form of functor, we can get a monad. And in our case, why do I want a monad in the first place? Because we are in Haskell and not in OCaml, so I can't just write proof streams somewhere without using side effects. So I can't have my auth and unauth as pure functions with the right types. Instead, I do that in a monad, and the side effect will be that, so the idea is I construct a monad, I write my functions like this lookup in that monad, only one version, and instead of having compiler versions as in OCaml to get the prover and the verifier, I have two interpretations of this monad into two concrete monads, and then one version will run on the verifier side and one on the prover side. So in our case, we want these two operations, auth and unauth. And so I define this helper data type auth f for functor. So, and I have to write it in this continuation parsing style so that I can get the functor instance. So given a b, I can apply auth. So the capital A is for auth, the u is for unauth. And given an auth, I get a b. Okay, so this is just abstract that I want a monad where I have these two operations. And then I just use the free monad machinery. So I define the monad just as free. Normally, one would use a new type wrapper. Now, for simplicity's sake, I just have a type synonym. So the monad, I call it auth m, and it's just free of this thing. And then what you normally do, once you have done that, you write convenience functions so that it's easier to use these constructors. So now I can write auth and unauth using these two operations in my functor. So now I have constructed a monad that has these two additional operations. I mean, they don't do anything. It's a free monad, so it's just syntax. But now I've constructed a monad that has this operation A, from A to auth A, and unauth from auth A to A. Okay, but I mean, so far nothing has happened. I just set up the syntax. Now, how do you use that for our example? So you slightly have to modify the tree type. So the idea is basically wherever you have recursive positions in your original data type, you will wrap that in auth, which then has the effect when you serialize it, it gets cut off there and it's efficient. So in this example, the tip stays as it is, but the node, instead of directly the children being trees, it's now auth trees. But it's still very similar to the original one. And my lookup function is now also almost the same as the very first example I had, the simple one without prover and verifier. I mean, the only difference is now I'm in this monad. And before I can do anything with the tree, I first have to remove the auth. So I have to do an unauth to get, I mean, because I'm given an auth tree, so I unauth to get the tree. And then I can do just exactly the same that I did before in my simple lookup function. Right, so I only have to write this once. But so far, of course, nothing has happened, nothing interesting. It's just syntax. So now the interesting part starts where I write interpretations of my monad for the prover and the verifier. So the prover first. And here, I mean, so again, for simplicity's sake, I just assume that I have a monad writer builder. Builder is this type from the byte string library that allows you to efficiently build byte strings. So it's basically, I can write as a byte string. And interpretation, so from this abstract auth m monad that I constructed into such a writer monad. So this is for the prover. So return is boring. Authenticate also doesn't do anything. So I simply take the A. So that's the interesting part is the unauthorized or unauthenticate, sorry, where I earlier said that that writes the wrapped value into the proof stream. So that's here. So when I hit an unauthenticate of an A, then later I return the A, but before I return the A, I write this A and code it into the proof stream. Okay, and then I can, to actually use that and have examples, I use the writer from the MTL library, which one shouldn't because it has a memory leak, but for simplicity, so using this, I specialize that to this writer type, and then I can just get my answer A and the byte string, which is proof.
Why does run prover not simply run a builder?
Because this is, okay, it wouldn't, probably it wouldn't have to return the A, but maybe you want to use the A later on the prover side as well, if you chain these functions. This could be an insert. Instead of lookup, it could be an insert that modifies the data structure, and then you need the result on the prover side as well. Right. So that's the prover side. And on the verifier side, things can go wrong, of course. So I introduced this, this type for exceptions. So there are two things that can happen. There can be a deserialization error. That I mean, I get some arbitrary byte string. Nobody guarantees me that it was generated by the prover. Or it can actually be a hash mismatch. So now, for the verifier, so I assume I have a reader for byte string on the verifier side, that I get access to my proof stream. And I can throw these auth error exceptions. So I have a monad error. And pure and auth are, again, boring, and the interesting part is, except that auth hashes. As I said before, on the verifier side, authenticate is hashing. And the interesting part is the unauthenticate. So I ask for the proof stream, then I deserialize it. That can go wrong. In that case, I throw an error. If it doesn't go wrong, this BS primes the rest of the proof stream, which I will then use to go on if everything goes well. This is the deserialized value I need. And, sorry. Oops. Right, and now this is the check. So I check that the age I was holding here is indeed the hash of what the prover sent me in the proof string. And if yes, then I continue with the rest of the proof stream, and otherwise I throw this mismatch error. And then I can also write a convenience function that just uses an either in the reader monad, and so it gets the computation and the byte string, and then either returns an error or the answer. And right, and then to redo our example, it's now a bit nastier to build the tree, because I now have to build it in this monad, but it's just noise. So, so I create the tree, I mean the three leaves, T1, T2, T3, and I always have to wrap it in auth, and this internal node, so I take those two and authorize that, and finally I get my root. So this is, I run prover on that, so I get the prover version, and then I use toHash to get the verifier version. So the prover version basically looks like our original tree, except it has this P noise everywhere. That's because I inserted these auth types. And the verifier version is just the hash, which corresponds to the Merkle root. And right, and now we can check it, that it actually proves something. So in this example, we we extract the proof, so we run the prover on this path with the lookup function on that tree that we just constructed, and just in this case, we are really just interested in the proof. And then we run the verifier on the same computation with the same arguments with that proof, and the mechanism says, yep, it's correct, and the answer is 2. And if I try to cheat again, like I did before, by using a different path, then it says, no, hash, mismatch. So it works. And just as a remark, you probably in practice would do that a bit more sophisticated. So there's also this monad transformer version of free. So instead of just defining a monad, you could define a monad transformer auth T like this. And right. And as I mentioned before, you can also not do free monads at all. I mean, there are several versions. You can use operational instead, or these co-density monads that are more efficient in certain situations. Or you also don't have to use free monads at all. You can use type classes, for example, define a monad auth type class, and then, or whatever. And there are several ways to do this. And just another simple example, lists. If I want to, I mean, I claimed that now we can do generically all sorts of data structures. So the easiest that we can think of that's interesting is lists. And so an A-list, authenticated list, would just be either empty or cons. But again, I wrap the recursive part into an auth. That's basically the only difference to our lists that we all know and love. And then I can implement, I can see that as a stack where I have push and pop. So push is just so I push an element, I just cons it, so I cons it, and then I have to authorize the result. And pop is supposed to get an authenticated A list and then return maybe A if it was not empty, return the head and the tail of the list. So I included this example because in the previous example I only used unauth. So this is an example where you would use auth. Unauth is basically just for querying a data structure. Auth you will need when you build one. So here you build up the list. So pop we unauthorize, and then we just pattern match whether it's empty or not. And want to just finish quickly with a very short demo.
We're basically out of time, and if you want to
1 minute
have one or two questions, then
okay, I don't have to show the
stop
demo. Right,
I mean,
let's do the questions instead.
Yeah, okay. Then
And it's also on GitHub at my repository. Yes, thank you very much.
Thank Lars. Okay, are there any questions? Otherwise, we can do the demo after all. Yeah.
Your first example with the Merkle tree, where you're trying to verify the signature from the top hash and pass all the data. How is it linked to the zipper? Aren't we reconstructing a tree like from a zipper, except that we don't have the data, we have the hash? And does it generalize to other data structures? This kind of.
That's a good question. Whether it always has something to do with zippers. You mean probably it has something to do with zippers? Okay. Yes.
Yeah, I was going to ask something very similar, but I mean, when you said generic, I was, of course, I mean, I'm biased. I was thinking about something slightly different, and I think there is a general principle for turning a data structure into a authenticated data structure that could also be implemented. So you have basically built up all the tools for this, but not done that step, which would be nice to add, which would then also I think have a story. That
could be done with generic programming.
On paths and zippers and so on, so everything comes together. Anything else? No? Okay, then let's thank Lars again.
Thank you.